Hey everyone, welcome! Today we're opening up Chapter 3 and building a practical map of generative AI. And honestly, this topic gets exciting very quickly. GenAI can write, design, compose, simulate, and even help explore new scientific possibilities. But here's the important part. A great demo is only the beginning. We're going to start with what actually makes AI generative. Then we'll explore the different output types, the technology stack behind them, and the algorithms that make everything work. After that, we'll get into operations, validation, cybersecurity, and ethics, the pieces that turn a clever experiment into something people can genuinely trust. So think of this session as a guided tour. We'll move from the big idea to the real-world decisions teams have to make. Ready? Let's start with the core question. What makes GenAI different from the AI systems we already know? Okay, here's the big idea. GenAI learns patterns and then uses those patterns to create something new. Traditional AI often predicts, classifies, or detects. Generative AI goes one step further. It can produce a fresh paragraph, an image, a voice, a video, a design, or even code. There are 4 traits to notice. First, creative output. The system makes an artifact, not just a prediction. Second, learning from data. It studies huge numbers of examples and finds the relationships inside them. Third, variability and novelty. Ask twice, and you may get 2 different answers. And fourth, versatility. The same broad approach can move from language to science, media, and design. Now, pause on that equation at the bottom. Pattern learning multiplied by creative synthesis. That's the magic, and also the limitation. The model is not imagining from nowhere. It is remixing structures it learned from data. Next, let's see just how many forms those outputs can take. This is where the range of GenAI really comes alive. Chapter 3 identifies 11 output classes, but instead of memorizing a long list, let's group them by what they help us do. First, language. Generating text, understanding meaning, translating, answering questions, and predicting what comes next. Then media. Images, speech, music, and video. This is the creative side most people notice first, because the results are immediate and highly visible. Next, interactive generation. Multimodal systems combine text, images, audio, and other signals, while game content tools can create environments and experiences that respond to users. And then we reach science and data, which is seriously fascinating. GenAI can propose molecular structures for drug research and create synthetic datasets that support development without directly exposing sensitive records. So before asking, which model should we use? Ask, what exactly are we trying to generate? That one question keeps the technology connected to the actual problem. Now we hit one of the most important ideas in this whole chapter. Capability, security, and ethics have to move together. On the left, we have rapid technical progress. GANs, VEs, transformers, diffusion models, and increasingly rich generation across text, images, audio, video, and science. Amazing, right? But the exact same capabilities can be used for phishing, deepfakes, fraud, or misinformation at scale. That's why security cannot wait until after launch. Teams need detection, monitoring, and defenses that evolve as fast as the models do. Then we have governance, bias, privacy, consent, misuse, and accountability. These are not optional policy topics sitting outside the technology. They directly affect whether people trust the system. So the takeaway is simple but powerful. Every new capability expands the opportunity surface and the responsibility surface. Innovation creates value only when security and ethics are built into the journey from the beginning. All right, let's talk tools, because the GenAI market can feel like a giant wall of names. A cleaner way to navigate it is to choose among 3 layers: build, manage, or integrate. Frameworks like TensorFlow, PyTorch, JX, Keras, and Schenner give teams deep control over model design and training. That flexibility is powerful, but it also demands expertise and computing resources. Managed platforms, Google Cloud AI, AWS SageMaker, Azure Machine Learning, and IBM Cloud handle more of the infrastructure. They help with training, hosting, scaling, security, and MLOps. Then we have libraries and services, such as the OpenAI API, Hugging Face Transformers, and Magenta. These can dramatically speed up application development by providing pre-trained or specialized capabilities. Here's the pause before purchasing moment. There is no universal best tool. The right choice depends on requirements, skills, scale, security, cost, integration, compliance, and support. Choose the level of control your team can realistically operate. A GenAI model does not stay useful just because it worked once in a demo. It has to live inside a continuous operating cycle. Data, build, test, deploy, monitor, and improve. MLOps is the backbone here. It handles versions, testing, deployment, monitoring, retraining, documentation, and governance across the machine learning lifecycle. But MLOps has a supporting cast. AIOps watches the IT environment, detects anomalies, diagnoses issues, and can automate remediation. DevOps moves the surrounding software through integration, testing, deployment, and feedback. DataOps keeps the data pipeline clean, reliable, integrated, and governed. ModelOps focuses tightly on production models, their versions, performance, explainability, and retirement. It sounds like a lot of ops. I know, but each one answers a different operational question. And here's the key point. Production GenAI is a system, not a file sitting on a server. These disciplines work together to keep that system reliable, secure, and continuously improving. Now, for the algorithm landscape. And this is where people often ask, which model is the best? The honest answer is, best for what? If realism is the goal, GANs and diffusion models are strong choices for high-quality images and transformations. The trade-offs can include heavy compute, difficult training, and deepfake risk. For learning compact representations, VEs and RBMs help with reconstruction and feature learning, although the outputs may be softer or harder to scale. For sequence and context, transformers and autoregressive models power text, translation, code, and speech. They are incredibly capable, but they can demand huge amounts of data and compute, and they can inherit bias. Flow-based and energy-based models matter when probability structure or physical systems are central. Hybrid and multimodal models combine strengths, but they also increase integration and governance complexity. So don't chase the trend. Start with the constraint. Realism, context, probability, compute, privacy, or control. The problem should choose the algorithm. This slide makes a point I really love. Quality is a stack, not a score. For images, metrics like IS, FID, and SSGEM examine quality, similarity, or visual structure. For text, BLEU, Rouge, and Perplexity measure different aspects of language performance. Classification can use a confusion matrix or F1 score, and translation may use Meteor. Useful? Absolutely. Complete? Not even close. We also need robustness tests. Cross-validation and holdout testing check generalization. Adversarial testing pushes the model with difficult or malicious inputs. Zero-shot evaluation asks whether it can handle unfamiliar tasks. And then comes the human layer: judgment, fairness, bias analysis, and safety evaluation. These checks capture qualities that a numerical metric may completely miss. Here's the pause-worthy takeaway. No single measure proves that a model is good, fair, safe, and useful. Validation has to combine evidence, and it has to continue after deployment because the data, threats, users, and model behavior keep changing. Now, let's bring all of this into the real world. And the variety here is genuinely exciting. Automated journalism can produce rapid, data-driven reports, but it raises questions about transparency and accountability. Personalized learning can adapt content to each student, while privacy and equitable access remain critical. Predictive maintenance can reduce downtime and extend equipment life, provided the sensor data and predictions are reliable. Drug discovery can accelerate the search for promising compounds, but every candidate still needs scientific validation and regulatory evidence. Fashion tools can generate new designs and help reduce overproduction, while copyright and originality become complicated. Customer service chatbots can operate around the clock, but accuracy, disclosure, and privacy really matter. Generative art expands creative possibilities, while challenging ideas about authorship, consent, and provenance. See the pattern? Every use case creates value and immediately introduces a guardrail question. Responsible GenAI is not about slowing innovation. It is about making that innovation durable, trustworthy, and safe enough to scale. Let's wrap everything into 5 practical questions. First, what must be generated? Define the modality, context, novelty, quality, and speed you actually need. Second, what data can support it? Look at quality, rights, privacy, representation, and versioning, not just volume. Third, which model fits the constraint? Balance capability with compute, control, interpretability, and risk. Fourth, how will it operate? Decide how MLOps, DataOps, DevOps, ModelOps, and AIOps will support the system after launch. And fifth, how will trust be proven? Combine metrics, stress testing, human review, fairness analysis, and safety controls. That final line is the one to remember. Build the system, not just the demo. A demo shows what is possible. A dependable GenAI capability shows that the data, model, platform, operations, cybersecurity, ethics, and validation can all work together. And that integrated mindset is what turns curiosity into lasting value. Thanks, everyone. This is where the real GenAI journey begins.